essentially what we've learned so far can be condensed in one problem, a titration problem. Okay, this is it right here. It can be condensed to this. So what have we learned so far in acid-base chemistry? Well, what we've learned is that if you have a weak acid, you can calculate the pH, because that weak acid will dissociate. It's going to form hydronium ion, and you can calculate that hydronium ion by that shortcut um, technique I showed you. Okay, so that's one of the things that we've learned so far, is that if you have a weak acid, you can calculate the pH. We've also learned from our last discussion, okay, that if you have an acid and its common ion in solution, you can just go straight to the Henderson-Hasselbalch equation, okay? As long as you know the concentration of the acid and the conjugate in that solution, you can go straight to the Henderson-Hasselbalch equation. That's the other thing we learned. The other thing that we learn is salts. We know that if we have a salt, it breaks up into its ions. And now we can take that ion that forms and look at how it reacts with water. If you have something like sodium acetate, for example, okay, sodium acetate, you put it in water, it'll break up the sodium and the acetate. You can calculate the pH of that solution, because the acetate will react with water to form acetic acid. Why does it do that? Because it's the conjugate of a weak acid. Conjugate of a weak acid is a base. The base will react with water and form that weak acid again. Okay, that's so true of weak acids and weak base. They want to reform. They want to reform. So we learned that when we talked about salts. And then the last thing that you guys know, or maybe I didn't tell you this, but in the presence, if you have a strong base and you have weak base on top of that, a strong base in the presence of weak base, the pH of that solution is dictated by the strong system, the strong base. You don't even have to worry about the contributions from the weak system, because it's not going to add up. And we actually saw that in polyprotic systems. Remember phosphoric acid? Phosphoric acid, you have a system where it peels off one hydrogen, then that conjugate peels off a second hydrogen, and then that conjugate peels off a third hydrogen. But what was the concentration of the hydronium ion from that three reaction system? Well, the concentration all came from that first reaction, because the Ka from that first reaction was so much bigger than the Ka2 and the Ka3, that the contributions from the hydronium in the second reaction and third reaction was minuscule, So if you remember these four concepts, these four things that I talked to you about, you know how to do this calculations of titration curve. You know how to do that. And keep that in mind as we dive into this particular section. Okay, we're generating titration curve. You always know there's two components in a titration curve. There's actually more, but two major components, two major players, okay, in the titration curve. The first one, oh, here's the picture already. The first one is the analyte, okay, analyte. And the second one's the titrant. If your titration curve starts below 7, then remember, you are monitoring the analyte. You're looking at that with a pH meter. If your pH is below 7, that analyte's an acid. If your titration curve is above 7, then that analyte's a base. Okay, this is where 0 titrant is added. Now, what will happen is that if you have an acid, it'll become less acidic and more basic, because the titrant that you're adding has got to be an opposite. Otherwise, you don't get a neutralization reaction. So eventually, what will happen is that you get to the equivalence point. That's where the moles of your acid and the moles of your base are equal. That's your inflection point in your titration. And then you get excess titrant, Where it plateaus will give you a rough idea of what concentration of that titrant is. Okay, but you know that your titrant is going to be a base because you're making the solution more basic. The pH is going up. Here, you know your titrant is an acidic because you're making the solution, as you're adding the titrant, more acidic. Where it levels off will give you a rough idea of what the concentration of that titrant is. So those are just things that you need to be aware of when you look at a titration curve. Okay, so there are 4 regions in a titration curve. One is where you just have the beaker and you've got your pH probe in there and you want to know the pH. That's just an equilibrium problem. That's just a weak acid or weak base problem. Okay, that's, like I said, that's why I talked to you guys in the beginning of what you already know. In this particular case, what you can do is, if we have a weak acid titrated with a strong base, you always want to make your titrant strong, okay, and opposite to your analate. Why? Because you can, that's what you can control. Why make it weak and make it problematic for yourself? I won't even give you that in an exam question because it's not realistic. I won't tell you, generate a titration curve of a weak acid, titrate it with a weak base. It's not realistic. That's not what we do in lab. So don't expect to see that in an exam, okay? Don't even see it in your MCAT question because that's not a realistic problem. What is a realistic problem is that you have a weak acid, weak base, you got some chemical and you're analyzing and you're adding some titrant that you can control. And that generally would be a strong acid, strong base. So when you have this and you add, this is 0 before you even start the titration, guess what? This, just cut to the chase right here. You just do this. You just use that equation. You get the pH right away, or at least you get your hydronium ion concentration right away. Okay? Before the titration start, just calculate the hydrogen ion of that analate using that equation. Okay? Buffers, super easy, because what will happen now is that you're going to add a certain amount of base into your analate, and some of it's going to get, some of it reacts. So what you have here is you've got the acid and its conjugate present in the same solution. Guess what? If you know these concentrations, then you can just do this. Just use the Henderson-Hasselbalch equation, okay? And that's going to be in the region where you've got both the acid and its conjugate present, and that's a very big region in the titration curve. Then you get to the equivalence point. We call that hydrolysis. At the equivalence point, all the acid is wiped out because you got equal amount of acid and the base. Guess what that acid converts to? It converts over to its conjugate. So now what you have is like the salt problem that I mentioned. If you know this concentration, then that chemical will react with water to form hydroxide and its conjugate. Hydrolysis. Remember I talked to you guys about hydrolysis last time? It says it's reacting with water. That's what when you neutralize all the acid and it converts over to its conjugate, that conjugate is the only thing left. But when we do our thought experiment, that now will react with water through hydrolysis. It's not a buffer. Make sure you know it's not a buffer. You can't use the Henderson-Hasselbalch equation. What you can do is this right here. And guess what? You're forming hydroxide. That's a Kb problem. And you can do this. Hydroxide ion concentration equals the square root of Kb times the concentration of that base. You can do that. Okay? But remember, when you're doing a titration curve, you don't want to plot POH. You want to plot pH. So what I will see a lot of times, this is what I will see a lot of times because you guys aren't thinking, okay? You don't want to do that. I need to erase this real quick. This is what I will see in a titration curve. You will do this. You have a very nice start. You know what that is. And then all of a sudden at the equivalence point, it drops all the way down. If you have a disruption in your titration curve and it goes up and it drops, the reason why it drops is because this is your pOH value and not your pH value. If you convert that to pH, it'll be up here. Okay, it'll be up there. So you're just doing mechanically without thinking. You're going to calculate the hydroxide ion concentration with that, but you want the pH. So calculate the pOH and then use pH plus pOH equals pKw. Okay. Then we get this right here. We get this right here. I need to clear my, when we have that right there, what will happen is that you're going to be adding excess base. All you have to do is figure out how much that excess base you have, the moles, and know, because the volume's constantly changing when you're adding titrant. Divided by the volume total, and that'll get you your hydroxide ion concentration. You can just calculate the pOH from that, and then calculate the pH from that. And you're done. Those are the 4 things that you need to remember when you do a titration curve. Not hard, guys already covered the fundamentals. You did. You already covered the fundamentals. You just have to string it together in one big problem. And yeah, the one big problem might be intimidating, but make sure you understand the little bits so that it's not intimidating. It's not intimidating. So let me clear this because I want to make sure that I review this for you guys. Okay. This is basically it right here. Okay, this right here would be a titration curve for this particular discussion. It looks like that. This point right here is that equation right there. Once you add titrant, this region right here, that's your buffer. Use the Henderson-Hasselbalch equation right there. This equivalence point right here, that's the inflection point. That's your hydrolysis. That's when all the acid converts over to its conjugate. That's this equation right there. Notice that these 2 equations look very near identical. But one's for hydronium, the other's hydroxide, because at the equivalence point, you've converted all the acid to its conjugate, and now the solution will be basic. Yes, the solution will be above pH 7 in this particular case. Because remember, when we have a salt, if you have a salt made of the conjugate of a weak acid, the solution is going to be basic. Look it up. We talked about that last time. And then this right here, that's just the hydroxide ion concentration that is in excess. It's just a hydroxide ion concentration in excess. So this is a spreadsheet that I generated. These are the functions in Excel, okay? It's in the lecture notes. So when I need to generate a titration curve, I have something like this, and everything's sort of mathematically based anyway. Let's take a look at this problem. Okay, I've got about 15 minutes, so I'm gonna somewhat summarize it for you. In this particular problem, I have, this is the titration curve. Notice this is region 1, this is region 2, this is region 3, this is region 4. Those are the 4 types of calculations I showed you. So that's what we are looking. That's basically what we talked about last time. So this problem right here is a titration where I have potassium hydroxide is my titrant, and hypochlorous acid, HOCl, it's a weak acid, okay? If I didn't give you hypochlorous acid, suppose I trick you. Not that I would, but if I did, and I made this HO2,3Cl, guess what that is? That's H ClO3. Okay, it's not a weak acid, it's a strong acid. So all of the things that you see right here doesn't apply, because this is a strong acid, strong base situation. Don't get tricked. That's why you got to remember it's 7 strong acid. If I gave you HClO3 or HClO4, there is no Ka's associated with that. If I gave you HClO2, there is a Ka associated with that. HClO, this is it, HClO, there is a Ka associated with that. And then you have to go through this exercise that I'm talking about, okay? So the first question that you will usually see is that, okay, we're doing a titration. You know what the titrant is, it's a strong base, and you know what the analyte is, it's a weak acid. And I need to get the pH values at 0%, 50%, 95%, 100%, and 105% of the equivalence point. Well, the equivalence point is where the moles of the acid and the moles of the base are equal. That's the equivalence point. So I need to know what the equivalent volume is, because if I know what the equivalent volume is, then I know exactly how much titrant I'm adding to calculate the pH, because you need to know that, okay? So in this particular problem, let me move on. It says that my weak acid is, I've got 10 milliliters, 10 milliliters. Notice we're dealing with milliliters, so you're going to be dealing with millimoles, and it's 0.4 molar. Guess what? 10 times 0.4, that's just 4 millimoles. 4 millimoles. 10 times 0.4, 4 millimoles. Okay? And we have a titrant, KOH. It also has the same concentration, 0.4. This is a super easy problem, because at the equivalence point, I would need 10 milliliters, because at 10 milliliters of 0.4, I would also have 4 millimoles of KOH. So the equivalence point here, 100%, that would be 10 milliliters. That means 105%, 10 times 10, 105, that's 10.5 milliliters of KOH. 95% would be 9.5 milliliters. 50% is 5.0 milliliters, and 0 is just 0. So you just figure out what the equivalent volume is for your titrant, because that's 100%. And then if the question is, what is the pH at 75%? Take 75% and multiply by the volume at 100%. That'll give you the volume at 75%, okay? So this problem, it's not so difficult, because then I would need to know the pH. This is the volume right here, and I would generate a pH here, and the volume would be, this would be the volume of titrant. That's not the volume of the solution though. Okay, the volume of the solution will vary, but the volume of titrant will be 0, 5.0, 9.5, 10.0, and 10.5. Each time you're adding it to 10 milliliters. So 0 plus 10 is 10. 0 plus 5 is 15. So the total volume here, V total, because remember your analyte is 10 milliliters. So this would be 10. This will be 15. This will be 19.5. This would be 20. This would be 20.5. Why is the total volume important? Because whenever we're dealing with equilibrium, it's molarity that we use, not moles. Moles is for stoichiometry, but when we deal with equilibrium, mass action expression, Henderson-Hasselbalch equation, it's molarity. That's why you need a total volume. And the total volume will constantly change when you're doing the titration. Okay, so this is our job. This is our job, to calculate the pH of this. Okay, one thing you should know, this is a GIF. At 50%, pH equals pKa. 50%, that's this right here. I know the pH of that because I know that the pKa of this acid is 7.46. So that's going to be 7.46. I'm not even going to think about it. Why? Because according to the Henderson-Hasselbalch equation, when I have equal amount of the acid and its conjugate. That's at 50% titration. That's, let me say that again, at 50% titration, not 100%, 50% titration. You have equal amount of the acid and its conjugate. If they're equal amount, that goes to 1, log of 1 goes to 0, pH equals pKa. That's this region right here. pH equals pKa. Now I tell you this now, and you guys are going to forget. You're going to say here is where pH equals pKa. No, that's the equivalence point. That's where hydrolysis occurs. Okay, pH does not equal to pKa at the equivalence point. Only at a 50% point. 50%. So you know that 10 milliliters is 100%. 5 milliliters is where pH equals pKa. You guys are going to have to know this for lab. Okay, when you do your unknown. So I already got a point. I got some points right now because I've got data. Okay, so yeah, it's messy here, but that's how you're going to have to set this up. That's how you're going to set this up. This portion right here, that's just, well, let's take a look. Okay, let's take a look. At 0%, all I need to do is really this. H plus equals Ka times the acid concentration. I know the acid concentration was 0.4. I know that the Ka was, what was the Ka? 3.5 times 10 to the minus 8. And now I can calculate the hydronium. So here's my calculator. Let me just do this real quick without looking at the answer. And I'll show you that comes pretty close. Okay, comes pretty close. I'm going to take 3.5 to the 8 negative. I'm going to multiply that by 0.4. And then I'm going to take the square root of that. That number comes out to 1.18 times 10 to the minus 4. And then I'm going to take the negative log of that. So I get the pH. That comes out to 3.92. Took me less than a minute to do that. Okay, or you can go through the ICE table. 3.93 if you are really going to. I actually solved this using a quadratic, I think, but 3.969. That translates to 3.93. Oops. There it is. Okay, don't make it hard. It's not. I'm showing you all the shortcut I teach my analytical students, analytical chemistry students. Okay. These questions are all the same since 20 years ago. So don't make it hard. Don't like have a, don't get exhausted in your brain because it's not that difficult. Okay, here it is right there, 3.93. ICE table gave you the same thing. Same thing. Okay, so you got your first point and you got your second point right here as well. Let me move on. Okay, 50%. Don't even bother doing a calculation. You should know that already. Okay, but here it is. I'm going to show you the calculation anyway. Okay, 7.46. That's what it'll be at 50%. Okay, so again, it's not hard, but a lot of you make it hard. Then you get an ulcer because you're frustrated. Here it is. This is the Henderson-Hasselbalch equation. This is the ICE table. Gives you the same answer. Gives you the same answer. Now I've got a second data point. Second data point, okay? What happens at 95%? 95%. We're still in the buffer region. We're not at the equivalence point, but we're still in the buffer region. You have to do a little bit of calculation on this. You have to know what acid you have, and you need to know how much conjugate is formed. So you have to do this, okay? You've got the acid and you know how much base is added. The first part has got to be stoichiometric because the base is going to dictate some of the acid reacts. So if you got 4 millimoles and then you're adding 9.5 milliliters of 0.40 molar KOH, then that comes out to 3.8 millimoles. Do the math, 3.8. It's your limiting reagent. That's going to demand the 3.8 of your acid reacts, which means that it forms 3.8 of the conjugate, 3.8 of the conjugate. The amount that reacts is going to form the conjugate. Now we have the conjugate is 3.8 millimoles. The acid, 4 minus 3.8, 0.2 millimoles. Okay, it's all sitting in the same volume. It's all sitting in the same volume. That volume would be 19.5 milliliters. Why? Because you had 10 originally and you're now adding 9.5 milliliters of titrate. This is a buffer. Why is it a buffer? Look, they're both present in the solution. I can just go to this equation right here. pKa plus the log. My conjugate is 3.8 over 19.5, but why divide by 19.5? Because I'm also going to divide by 19.5 in the denominator, so they cancel each other. It's just 3.8 over 0.2. And if you do that, okay, you should get a pH of 8.73, and here it is right here, okay? Using the Henderson-Hasselbalch equation. I probably rounded off too much in one of these, but hey, that's pretty close, okay? You're gonna get that. As long as you have both pairs present in solution after the stoichiometry, you've got a buffer, go straight to the Henderson-Hasselbalch equation. Go straight to the Henderson-Hasselbalch equation. It'll save you grief, okay? So now I got 3 points. I got 3 points right here. Let me clear this. There it is. That's a 95%, that's a 50%, and that's the initial. Now we have the equivalence point. We have the equivalence point. At the equivalence point, this 4 millimoles now converts completely over to the conjugate. But the volume is now 20 milliliters. So at the equivalence point, 100%, the 4 millimoles of acid converts over to the 4 millimoles of conjugate. The 4 millimoles in 20 milliliters, total volume. That's total volume. You need the total volume here because you need to know the concentration in molarity. But once you have that, okay, once you have that, then just do this. Hydroxide ion concentration is equal to the square root of the Kb times this concentration right there. Because all your acid is now the base. And that's just a weak base problem. That's just a weak base problem. Okay, it's hydrolysis. So let me show you that calculation real quick. Here it is. This is 4 millimoles, and if you divide it by 20, that's 0.2 molar. Now, I gave you the Ka. How do you calculate the Kb? Remember, the Ka times Kb equals Kw. So you can use that. And so that's what I will have right here. This is my Kb. Let me clear this for you. Kb equals Kw over Ka. That happens to be, what is that value? 2.8786 times 10 to the minus 7. And what I did here was, well, let's figure it out. Hydroxide ion concentration is equal to 2.86 times 10 to the minus 7 times 0.2. Let's see what we get when we do this shortcut. So I'm going to take 0.2, multiply it by 2. Remember, this is Kb. Okay, that's Kb. 2.86 to the 7 negative. Multiply that out, and then take the square root of that. I have something of 2.39 times 10 to the minus 4. That means my POH is equal to, take the negative log of that, 3.62. But if you plot this in your graph, you're going to get a titration curve that looks like this. Like I said, it's going to drop. Remember, this is POH. You got to subtract 14 from that. And now my pH is 10.37. 10.37. Hey, that's pretty close. Okay, that works. That works. I skipped all of this. I was able to use that just by using that equation. Just by using that equation. Finally, okay, finally, here it is. We got this 10.38. Okay, finally, what happens when we have excess? Well, this is the amount of base that did not react, 0.2. What is the total volume now? The total volume is going to be 10 from our analyte plus 10.5 from the titrant I add is 20.5 milliliters. So the concentration of that excess base that was unreacted is 0.2 millimoles over 20.5 milliliters. That concentration of hydroxide is just 0.2 divided by 20.5. That's 9.76 times 10 to the minus 3. That's my hydroxide ion concentration. If I take the negative log of that, no equilibrium involved now. That's just hydroxide directly. If I take the negative log of that, that happens to be 2.011, okay? But remember, that's POH. In order to get pH, you got to subtract 14 from that. That's 11.99. Look at the answer right there, 11.99. 11.99. Now, this chemical right here, that's a base. So that base will also produce hydroxide. But I'm going to show you in this calculation up here that the amount is so minute, you ignore it. So I'm going to clear this. This is the calculation for how much the conjugate produce in terms of the hydroxide when it does hydrolysis, because remember, you're going to have the conjugate in that solution. Look at the amount that you actually get. You actually have to solve this using the quadratic, and that concentration is about 6.64 times 10 to the minus 6. 6.64 times 10 to the minus 6 versus 9.76 times 10 to the minus 3 from the excess hydroxide. You ignore the contribution from this. You ignore that because it's not significant. It's not. So you have our last point, 11.99. Now you connect the dots. You connect the dots. Don't do this, okay? That's not a titration curve. It generally is going to be level right in the buffer region, and then it takes a steep incline right around the equivalence point. Okay, takes a steep incline. So think about that. This is, I know I went pretty quick, but it's not something new. It's what you guys already know. Okay, and I'll wrap this up probably first 15 minutes on Monday. But you guys know how to generate titration curve. Do the shortcuts that I have here, because it'll save you a lot of time. Okay. So sorry, it's 6:20. That's all I have for today. This, as soon as I find time between grading and doing other things, I'll edit this video and post it. So you guys. Last time we left off with a titration curve, and I hope you guys practice this enough times so you're not intimidated, okay? There's been too many times where I give a midterm and we just talked about it, we covered it in lab, and it's like a big chunk of the points in your midterm, and folks don't even try and start it, okay? And if you practice the titration curve that I talked to you guys about, as well as the one in the practice exam, it should be pretty straightforward because you guys already know the fundamentals of solving acid-base problem. Like I said, before you do the titration, well, you should figure out what volumes are going to be required. So you know the volumes of the titrant, and you'll be able to calculate the pH for those different volumes. That's always required. If you get the volumes directly, so I say, what is the pH when you add, say, 5 milliliters of titrant, 7 milliliters of titrant? That's easy, okay? Because all you gotta do is take the volume of the titrant and the concentration, and you have the moles, and you can figure out how much of the acid is going to react with that. But if I give you percentage, you need to figure out what is the 100%, what is the volume at the equivalence point, and then based on the percentage that you have to calculate, figure out the volumes from there. We did that example on lecture last time. You need to find the 100% because it's going to be the easiest approach. Okay, 100% is at the equivalence point, and at 50%, you just take the volume and cut it in half or multiply it by 0.5. Anyway, when you do the titration, there's going to be 4 strategies you've got to apply. And we talked about this last time. Here's a better slide on that, okay? First one is just a weak acid or a weak base situation if you're titrating a base, okay? If you're titrating a base that's your analyte, then you're adding acid to that. And the acid or the base, the titrant, will always be a strong acid or base, okay? Don't want to mess around with it being weak. It just complicates the problem. It should be strong. So this one's just a weak. In this particular case, we have a weak acid and it's being titrated by a strong base. So this is your analyte. This is a problem last time, and this is your titrant. So in that particular case, this is where you add no titrant. It's just a weak acid problem. Here, you're adding some titrant, and part of the analyte, that's the chemical you're analyzing, is going to get neutralized. Okay, and then some of your analyte, the acid in this case, is going to convert over to a base. So you have a common ion. When you have a common ion, use the Henderson-Hasselbalch equation. Okay, and then when you reach the equivalent point, all your original acid has now been converted over to its conjugate. Okay, all the original acid. So whatever moles you started with in the acid has now equaled the moles of the base. Of course, the concentration is not going to be the same because the volume that it sits in is going to be larger than in the beginning. So the concentrations is not going to be the same from the original acid you started. It'll be a little bit lower because the volumes are going to be a little bit larger. But nevertheless, if you know the moles of your conjugate base that forms and you divide it by the total volume, you now have the concentration of the base at the equivalence point. Of course, that base now is a weak base, and so it's going to react with water. But you can still do the shortcut right here. Okay, the shortcut is the hydroxide ion concentration. Why? Because the conjugate is going to react with water and produce hydroxide is equal to the square root of the Kb times the base concentration at that equivalence point. Okay, so you can do that, or you can do the ice table. It's up to you, and then you can get the pH at that point. And then when you go past the equivalence point, what you're doing now is just adding more titrant, and the excess titrant you add is just going to sit around. It's going to influence the pH of the solution. So all you got to really do is calculate that excess. And because the contribution from the conjugate, when you reach the equivalence point, it's going to be so minute. And I showed you how minute that was in our last discussion. But the concentration is going to be so insignificant that you can just calculate the excess of titrant you have, get the concentration, and then calculate, in this particular case, the hydroxide ion concentration, and then POH, and then pH. Remember that the titration curve that you are generating is pH. When you start calculating hydroxide ion concentration in the math, you got to make sure that if you got hydroxide, calculate the POH because that's the easiest path, and then subtract 14 from that. That's the easiest path. And then take that point and then plot it. So what you will get is something that looks like this. Okay, something that looks like this. A titration curve that looks like that. Okay, so again, practice it. For those of you in lab, you have a whole bunch of practice that you can do. For those of you who are not in lab, if you're taking a lab at Miramar College, you also have that activity that hopefully you've completed. If you're not there in any of the Miramar labs, then you should, there's a bunch of examples in the book as well as a bunch of examples, well, in the practice test. Okay, so let me move on. So when you have a strong acid and strong base, now I remember we didn't cover that. So it was up to you, but that's all based on stoichiometry. Don't look for a Ka or Kb for that. Why? Because they are strong acid, strong base. You've got sodium hydroxide, you're titrating hydrochloric acid with that, or you've got calcium hydroxide and you're titrating nitric acid with that. It's a strong acid, strong base situation. Well, what will happen is that your pH at the beginning, before you add any titrant, it's just based on the concentration of, in this particular case, the strong acid. Why? Because the strong acid, let's do this, will dissociate 100% of the time. So whatever the concentration of your acid is, that is equal to the concentration of the hydronium. All you've got to do is take the negative log of that and you get the pH. Okay, so that's basically what is happening for a strong acid, strong base situation. As you add titrant, as you neutralize it, pH really isn't going to change that dramatically. It'll slowly go up because you're neutralizing some of that acid. And now it's the excess is still your acid. Don't worry about the conjugate here, okay? That conjugate, like if this was Cl, is not going to react with water. Why? Because it's coming from a strong acid. In a strong acid situation, the anion is inert to hydrolysis. It's not going to react with water. Only weak acids will do that because the weak acid will generate base that are weak base and the base wants to react with water. Okay, strong acid will generate conjugates that are not basic at all. They don't want to react with water. So there is no reaction with that particular species. That's why you just have to figure out how much excess of your strong acid you have. This, of course, when you react it with hydroxide, will form water in the neutralization reaction. Anyway, the pH will go up because you're making it less acidic. And then you're going to get to a point where you have probably about a few moles of acid remaining, and when you add a few moles of base remaining, that changes the concentration dramatically. That changes concentration dramatically, and so you get a sharp change in the pH. You go from the hydronium ion being the dominant species to the hydroxide ion being the dominant species. But at the neutralization point, you don't have either acid or the base that you add in excess. They are equal. So the neutralization point, the pH is always going to be equal to 7, provided that the temperature is 25 degrees. Because at 25 degrees, Kw equals 1 times 10 to the minus 14. Okay, but it'll go through 7 because the pH is dictated by the auto dissociation of water, the self-ionization of water. And then when you pass that, what happens now is that you get excess titrant, and now the solution becomes basic. But it's going to have a very steep equivalence inflection point, okay? It's going to have a very steep inflection point because basically you go from excess acid, like 1 or 2 molecules, to 0 to 1 or 2 molecules of hydroxide. Okay, and so that's what this is. The important thing that you want to notice is that the equivalent volume, that's the volume at which you reach the equivalent points. That's the volume where the moles of your acid and the moles of your base are equal, is what you want to read. And you can see that in this particular case, let me clear this out. When you have, say, 19.99 milliliters to 20 milliliters to 20.01 milliliters In other words, 0.01 increment, the pH goes from maybe 3 all the way up to about maybe 11. So what does that mean? It means that the volume, it doesn't take a lot of volume to change the pH dramatically. If you're doing this in the lab, what you will have see when you reach the equivalence point is that the pH meter is jumping all over the place. It's going to fluctuate between here and here just because the electronics is not quite in sync. And so at some instance at the pH probe, the hydronium ion will be higher, the hydroxide ion will be higher, and you're mixing it. And so the pH at that point is going to jump up and down. But it's okay because you've already got the equivalent volume. You've already got the equivalent volume. Okay, and then as you add more base, of course, then it starts to tail off. The pH will become higher as you add more volume. Remember, this is the volume. This is the volume that you're adding in this particular axis. So as you go further right in the titration curve, the pH will go up and then it'll level off. It'll level off. Okay, that's what you see right here. Now, what you want to remember here is the following. Because the inflection point is so steep, whether you use an indicator like bromopheno blue or thymo blue or phenolphthalein, okay? Because remember, what are you trying to get in your titration curve? If you're doing an analysis, you're looking at the equivalent volume. Why is the equivalent volume important? Because if you know the volume and you know the concentration, then you can calculate the moles of your base, which is equal to the moles of the titrant you're analyzing. You're really after the equivalent volume. So look over here. If you use this particular indicator, you're still going to get the equivalent volume because the color will change right at that volume. If you use bromo-thymo indicator, you're still going to get the equivalent volume. Why? Because the color will change right at that pH region. Whether you use phenolphthalein, alizarian yellow, or bromo-thymo blue, because the inflection point is so steep, it really doesn't matter. But if you have a acid, say a weak acid that looks like this, okay, this is what your titration curve looks like. And some of you saw this in the lab. Then if you use bromo-thymo blue as your indicator, guess what would happen? You would say that the equivalent volume is somewhere around 5. Okay, you're going to get a false reading because remember, indicators are used to signal endpoints. Endpoints are where you stop titration because you can assume that the endpoint is equal to the equivalence point. If you use bromo-thymo blue, you're going to stop prematurely because it'll change colors right here, and then you're going to assume that your volume, equivalent volume is 5, when really it's not, okay? If you use bromo-thymo blue, then you're going to assume that your equivalent volume is here at about 17, 18 milliliters. And again, you're premature in the volume. Why? Because it's not in the inflection point. So you have to have an idea of what chemical you're analyzing. So you have an idea of where that inflection point is going to be so that you can pick the correct indicators. And in your book and in the lab manual, there is a list of indicators that changes colors at these regions. So an indicator that would change color right here would be the ideal indicator for this acid that I have right here, if you're doing the titration. Okay, because the inflection point is right here, so you want an indicator that changes color right around there, right where I showed you in green. That's one of the art in picking chemical indicators. We had to do that for the longest time before we had sophisticated electronic device. Of course, these days, even if you don't have an indicator and you have a pH meter, then that's good enough, which is what you guys did in lab, because then you can measure these pH values and then look at the curve. And then if you do a first derivative, what will happen? Let's say we have this as our titration curve. Okay. This is our titration curve. And the inflection points right here. What happens is that the slope of that line goes from positive, goes from positive, this is the slope of that line, to negative. It goes like that. So when the slope goes from positive to negative, if you take the change in the pH with respect to the change in the volume, you get what we call a derivative curve. The first derivative will look like this. It goes up when the slope is increasing, and then it goes down when the slope decreases. That would be the first derivative. And the function of the derivative curve is to figure out what is your equivalent volume. And then if you take the second derivative, it'll look like this. Oops, sorry about that. It'll look like this. And where it goes through zero is your equivalence point. And again, you take the first and second derivative, because really what you're after is the equivalent volume. So again, more information in terms of titration. And in chemistry, we do a lot of titration because we really want to analyze the chemical that needs to be determined in terms of its concentration. Okay, if you take analytical chemistry, you've got like, or doing any type of analysis, you've got like 3 titrations that you need to conquer. Your lab practical in this course, Chem 201, you have a titration. It's called a redox titration. Anyway, let me move on. So this is a weak acid, strong base situation. This is the example of what we did in our prior discussion. This is what you guys will be doing in lab this week. Okay, you're going to be given a weak acid and you're going to titrate it. Well, you're not going to do it. You're going to watch the video. And then from the features of that titration curve, you're going to determine the identity of that acid. Okay, so let me kind of help you along with that, and then I'll discuss this in more detail in the lab. So here again is the titration of a strong acid, strong base. This is the titration. It always starts out high of the weak acid. Why is it high? Because the pH is not going to be, it's going to be less acidic, in other words. When the solution is less acidic, the pH is higher, okay? So once you add the titrant and some of the acid converts over to its conjugate, you now have the buffer. That's why we have this buffer region right here. Okay, if you use, in this particular case, methyl red as your indicator, then you're going to, again, have a false reading on your equivalence point, because you're going to think that your equivalence point is over here where the color changes from like orange or pink to yellow, when really the pH is in that region, and so your indicator is responding to that. But that's not your equivalence point, because your equivalence point is way up here. Anyway, a weak acid will start out high. It'll reach the buffer region, and then at the equivalence point, for weak acids, the pH at the equivalence point is always greater than 7.0. Why is that? Why is the pH always greater than 7.0? Because when your weak acid's totally neutralized, what do you have? You have its conjugate present in solution, a base. And as a base, it'll react with water and generate hydroxide. And the solution will therefore be basic. So if you've got a analyte, that's the chemical you're analyzing, and it's a weak acid, expect the pH at the equivalence point to be higher than 7. Okay, it's going to be higher than 7 because that weak acid will convert over to its conjugate base, and that conjugate base at the equivalence point is going to react with water to generate hydroxide. That's why if this is 7 right here, the equivalence point is up here at about maybe close to 9. It'll always be that way. On the other hand, if you have an analate that's a base, a weak base, then what happens at the equivalence point, all that weak base will convert over to its conjugate acid. That conjugate acid will donate its hydrogen to water and generate hydronium. So if you have an analate that is a weak base, your pH at the equivalence point will be less than 7. If you got a strong acid, strong base, it'll be exactly at 7, 25 degrees. Okay, so I just want to point that out. Here's a really good curve to know. Why? Because according to the Henderson-Hasselbalch equation, pH equals pKa plus the log of the conjugate base over the conjugate acid. When these two are equal, the conjugates are equal to each other, this term goes to 1 and this term drops to 0. But that's at the 50% equivalence point, okay? 50% equivalence point. Not at the equivalence point, but 50%. So what you can do is you can look at this curve right here and you can say that, okay, if this is my equivalence point, okay, then halfway to that, right around here, that pH that you read right here is equal to my pKa. So for curve A, the pKa would be 1 times 10 to the minus 10. For curve C, you just want to look at the halfway point that pKa is going to be 1 times 10 to the minus 6. Okay. For curve D, that pKa will be 1 times 10 to the minus 4. For curve F, if you told me that that pKa is 1 times 10 to the minus 1, you'd be marked wrong. Why? Because that's a strong acid. Strong acids don't have a pKa, only weak acids. Okay, so please keep that in mind. But this is a good curve in terms of based on the series of acids that are being titrated. This would be your weakest acid. Why is it your weakest acid? Because it's got the smallest pKa. This would be your strongest acid. Among weak acid, of course, this is a strong acid by itself, but among weak acid, this would be your strongest weak acid. Now, suppose I ask you, which of these acids will have conjugates, base, that is the strongest? Okay. Again, let me rephrase that question. Among the acids, A, B, all the way down to F, okay? These will all have conjugates. This one will not be in the game because its conjugate is a non-base, okay? Because it's a strong, but let's say we go to E. If this is your strongest acid, then its conjugate will be your weakest base, okay? All you got to remember is that Ka times Kb equals Kw. If the Ka is large, then the Kb is going to be small because they have to multiply to 10 to the minus 14. If this is your weakest acid, then its conjugate is going to be the strongest base. Okay, the conjugate. The conjugates are always opposite. The conjugate of an acid will be a base. The conjugate of a somewhat strong weak acid will be a weak base. It's always the opposite. So keep that in mind in terms of questions that I've asked in the past. What I'll do is I'll give you a series of acid, and just based on the Ka, you know that this one's strongest and this is the weakest, but I won't ask you about the strength of the acid. I'll ask you about the strength of their conjugate base. So you have to keep that in mind. Okay, this is the strongest, so therefore that's going to have the weakest base. If that chemical has a stronger ability to give up its hydrogen, it's going to have the weakest ability to accept that hydrogen back. Okay, the chemical that wants to give up its hydrogen the most is also the chemical, the conjugate, that is not going to want that hydrogen at all. So think about that in terms of knowing trends. So let me go ahead and clear this real quick. Okay, so that's this somewhat important concept to know for those of you in lab as well. This right here, again, is the titration of a weak base with a strong acid. That weak base might be the acetate. Suppose I have acetic acid, C2H3O2. Okay, so I'm just going to abbreviate this HAC. That's a weak acid. But suppose I want to titrate the base of that. How would I introduce that in solution? I would replace the hydrogen with a metal. When that thing dissolves, it'll produce sodium, which is a spectator, and the acetate ion. Because the acetate ion is the conjugate of a weak acid, that chemical right there is a base. That's a base. So what does base want to react with? They want to react with acids, and they would form its conjugate and, of course, water. Okay, it's going to form its conjugate and, of course, water in this titration. So what you're going to do is you're going to take a look at the acetate, and acetate, when you have 0 titrant added, is going to react with water to form acetic acid and hydroxide. But that's just this right here. It's a Kb now times the acetate ion concentration. Use that shortcut equation I showed you. And now if you got the OH, you can get the POH. And don't plot POH because this is the pH scale. You got to take 14 minus the POH. And then you can plot it right there. Okay. And then, of course, this is the buffer region right here. And when you have a base, then the Henderson-Hasselbalch equation will look like this. The POH equals the PKB plus the log of the acid over the base, the conjugate acid over the base. And that's the equation you use for the buffer region. Look at the equivalence point. At the equivalence point, all the base now has converted to its conjugate acid because it's been neutralized, and then that acid will react with water to produce hydronium. So if it's producing hydronium, that pH is going to be below 7. And if 7's up here, then this right here is about maybe 5.1 or something. pH is going to be acidic at the equivalence point, just as we predicted. Okay, and then of course any excess acid will make that solution have a low pH, and that's what you see right here. So this is just the converse of what we talked about last time, but now what we're doing is we're analyzing the base and we're adding acid to it. Concept still the same. Shortcut equation still the same, except you're calculating POH. Always convert that to pH when you're doing a titration curve. Unless, of course, the titration curve is asking you to plot POH. So just think about what the question is asking. So let me move on this, okay? And that's just the verbiage of what I just talked to you guys about. So here you've got ammonium. Well, ammonium is an acid. Ammonium is an acid. So what you probably have here is ammonia. And ammonia will form ammonium when it reacts with the titrant. Okay, so you have ammonia, you're titrating it with hydrochloric acid. This is what the titration curve will look like. It starts high because it's basic. It ends low because you've got excess titrant acid in your solution. This is a titration curve, and notice there are 2 inflection points, one here and one here. So you probably know that if you have two inflection point, that means you've got two hydrogens coming off. This is probably a titration of a diprotic acid, diprotic. Something like H2SO3. When you take H2SO3, the acid, and you titrate it, this is the chemistry. H2SO3 in the presence of a base hydroxide, this is what will happen first. You don't neutralize both hydrogens in H2SO3. You neutralize you peel off the hydrogen one at a time. So the first reaction you will get is water plus HSO3. Okay, HSO3. You're only removing one hydrogen, the one that is going to be the loosely held hydrogen in H2SO3. Remember, H2SO3 is not H2SO4. H2SO4 is a strong acid. H2SO3 is a weak acid. It's a diprotic weak acid. So this is what happens. Now, when this moles and this moles are equal, then you reach the equivalent point right here. You reach the equivalent point right here when the moles of your hydroxide equals the moles of your original diprotic acid, then you reach the equivalent point. At that point, there is no more H2SO3. Everything has been converted to HSO3. Okay, HSO3. So what you need to do is you need to look at HSO3 and see how it reacts with water, and then calculate the pH from there. So that's how you get that. Now, you still have a buffer region right here. You still have a buffer region right here. Let me clear this. Okay, you still have a buffer region right here. Right here is your buffer region, and that's when your H2SO3 and HSO3 minus are present in the same solution. Okay, remember H2SO3 has a Ka1 and a Ka2. This is your Ka1 situation because it's the first hydrogen that comes off. So that would be the pH at the halfway point is going to be equal to the pKa1 plus the log of your HSO3 minus over H2SO3, the base over the acid, just because they're conjugate pairs. Okay, so that is what happens. Now, from this point on, what you have is HSO3 minus reacting with a base hydroxide, and then that's going to convert over to SO3 minus 2 plus water. That's the titration process in that second stage. Now, what happens at the equivalence point way over here, that's where the HSO3 minus has been completely converted to SO3 minus 2. Okay, has been completely converted to SO3 minus 2. The SO3 minus 2 now reacts with water and it'll generate hydroxide. It reacts with water. The water will donate a hydrogen to HSO3. You form the water will donate a hydrogen to SO3 minus 2. You form HSO3, but more importantly, you form hydroxide. That's why that solution is going to have a pH above 7. This buffer region right here, that's when the HSO3 minus and SO3 minus 2 are in the same solution. You're not looking at H2SO3 anymore. That's bygones. Here, you're just looking at that. And what you can do is you can calculate the pH using the Henderson-Hasselbalch equation. The pH at that point is equal to pKa2, it's that right there, because it's the second hydrogen that's coming off, plus the log of the conjugate base, SO3 minus 2 over HSO3 minus. that ratio of concentration. That's the Henderson-Hasselbalch equation that you would use for this particular situation. The concepts that I'm showing you here is no different from what we've talked about in the past, except now there's two stages. There's two stages. Anyway, let me clear this. This is just the discussion on that. Okay, the discussion on that. And again, you see two inflection point right here and right here. You see two inflection point. If you want to do the first analysis titration, you want to do this region right here. This is the buffer region. This is the equivalence point, and then this is past the equivalence point. If you want the second analysis, this is your starting point. At the equivalence point of your first, you start there, and then you end up over here. If you look at the equivalence volume, 80, well, if you're starting at, sorry about that, if you're starting at 40, then the 50% would be 60. At 60 milliliters, the pH equals pKa2, because that's halfway in the second process. And that in that particular case, your HSO3 is equal to your SO3 minus 2. That point right there. If you're starting at 40 at the equivalence point of your first hydrogen that comes off, and you reach the equivalent points at 80, then halfway in between there is 60 or 20 mils past 40, which is that. At that point, pH equals pKa. Okay. Here would be the same situation if you have a dibasic situation. We haven't talked about dibasic much, but dibasics comes from polyprotic acids. Let's take, for example, phosphoric acid. Phosphoric acid will do this. So you can see that phosphoric acid, just by its formula, H3PO4, is triprotic. Don't confuse phosphoric acid with phosphorus acid, H3PO3. H3PO3 is only diprotic. Why? Because that third hydrogen is not attached to oxygen. It's attached to phosphorus. So only two hydrogens in phosphorus acid is ionizable. But phosphoric acid, that's not the case. All three hydrogens are ionizable. So if we have PO4 minus 3, then PO4 minus 3 can generate hydroxide via water to produce HPO3 minus 2. And that can generate hydroxide to form H2PO, sorry, that's PO4 minus, and that could form H3PO4. So in other words, PO4 3 minus is tribasic because it can add 1, 2, 3 hydrogens. And depending on how many hydrogens you can add to a chemical, that's how you can tell what type of base, polybasic chemical you have. You can have a tribasic or dibasic or monobasic. In this particular case, PO4 minus 3 is tribasic. HPO3 minus 2, it's only dibasic. You do not, and I want to repeat this, you do not get this. This chemical does not exist. Okay, just I want to make that clear. So this right here is first hydrogen is added, second hydrogen is added. So you add a hydrogen to carbonate, you get HPO3. You add another hydrogen to bicarbonate, you get H2PO3. Okay. So make sure you understand the features of these different titration curve. You know, this is a strong acid titrated by strong base because you start low and you end high. This is a strong base titrated with a strong acid because you start high and you end up low. This is a weak acid titrated with a strong base because again, whenever your pH way past the equivalence point, when it starts leveling off, is 12 or higher, generally that's a sign that your titrant is a strong base right here. Okay, and then your starting point of your analyte is way above 1. It's like 2 something. That's a weak acid. So this is a weak acid titrated with a strong base. You're looking here. This is the equivalent volume right here. So right away, if this is 100 at 50, pH equals pKa for whatever the identity of this acid is. This right here is a weak acid titrated with a strong base. It'll drop, level off in the buffer. You reach the equivalent point and then level off as you add excess acid in this particular case. And these are situations right here where you have polyprotic system. This would be you see 2 inflection points, so it's diprotic. Here you see 2 inflection point, so this is dibasic. Okay, so make sure you understand how to read titration curves, because that's an important part of this particular understanding acid-base chemistry. And we're pretty much done. That's just a summary of how to solve titration problems.